Hello, this is my video submission for Lab 8. As done with the other labs, I'm going to scroll through our document and then I'll pan over to our model sim results. So starting off with the block diagrams, we got the program counter. This is the level 0 block diagram of the program counter, and it shows that the program counter has 3 inputs and it has 1 output. These 3 inputs consist of the program counter input, which is 8 bits, the reset, the clock, and then the output, which is also 8 bits. Scrolling down, we got the adder block diagram. So for the program counter, you're going to need a +4 adder, and this is our block diagram. It's 8 bits in, 8 bits out, and it's going to add +4 to the address that we're viewing. Scrolling down, you got the instruction decoder block diagram. This is our level 0 block diagram for it. You got the 32-bit input, and then you have all these outputs. You got the RD, the RS1, the RS2, and the IMM. The first 3 are all 5 bits, the final is 12. All of these block diagrams put together is going to give us our top level block diagram. Our top level block diagram is going to have a clock and a reset with all of these given outputs, the RD, the RS1, the RS2, and the IMM, 555 bits, and then 12. And we were able to successfully code this, and our model sim results show that. Let's see, we got the level 1 block diagram of the top level right here. Additionally, it goes into a bit more detail. So we got our program counter, which is connected. So we got our program counter, which is going to take a clock and a reset input, and it's also going to take the input, the program counter input, which is 8 bits. It's also going to go into the +4 adder to give us this kind of cycle. We're going to be able to cycle +4 for every address over and over and over again to view the instructions in each address. And that's going to go into the ROM, and all of this combined is going to go to the instruction decoder to give us our final outputs. The output of the ROM is 32 bits, and this is going to be the instructions for the R and the I type instructions. We're also going to need to input an address. Going over to our results, this is the model sim simulation. Let me make sure it's clear for you. I believe it's clear. If you can't see it, it's in our document. So to explain this top level design, this model sim is going to show the functionality of our program counter along with the instruction decoder, and it's going to be assisted by the ROM and the +4 adder. The program counter and the +4 adder are going to cycle through the instructions within the different addresses of the RAM by adding 4 to each additional address. Meanwhile, the ROM has the addresses of R and I type instructions. The final component, which is the decoder, is going to take these instructions, and it's responsible for giving us our main outputs that we're viewing here. The top 2 lines you see up here are the clock and the reset. These are going to go through and give us all of our values. And we got our outputs that we want to focus on right here, the bottom 4. So to talk about a little bit what happened with our test bench, we start off seeing if the reset input works, which it obviously does. And in order for the reset has to work to get the other values of the instruction address 0. Address 0 in the ROM is an add-I operation instruction, and it's going to add to A0 and puts the result in A3. Then we turn the reset off. Then the test bench outputs the RE, RS1, RS2, and the IMM of the instructions of the next 9 addresses in the ROM, which you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. This is because program counter's output depends on the positive edge of the clock. As you can see here, it's functional and it works exactly as we'd expect it to. Thank you.